Assalamu alaikum. My name is Abdul Hannan and my role ID is 191057. Today I am going to make a 2-bit comparator using AND gates, NAND gates, NOR gates and OR gates and XNOR gates. So in order to make 2-bit comparator, first of all we know the block diagram, truth table, Karnaugh maps and boolean expressions of 2-bit comparator. So you see my screen. Here is the block diagram for 2-bit comparator where I use 2-bit numbers N1 and N2. N1 consists of A and B and N2 consists of C and D. Here are the three conditions F1, F2 and F3. F1 consists of a condition where we see that N1 is equals to N2 and F2 consists of N1 when N1 is less than N2 and F3 when N1 is greater than N2. So from this block diagram now we make a truth table. Here it is the truth table of 2-bit comparator where the inputs are A, B, C and D and the outputs are F1, F2 and F3. Here you see that for every input only one LED glows at a time, and only it means that only one function runs at a time. From the truth table we see that when all the inputs are 0, F1 glows and F1 is 1 and F2 and F3 are 0. It means that when all the inputs are 0, both the N1 and N2 are equal, so F1 which is N1 equals to F2 is on while the other two are 0. Similarly from the other inputs we see that when the N1 is greater then F3 is 1 and when N2 is greater then F2 is 1. Now from this truth table I gonna make a Karnaugh map for 2-bit comparator. Here you see the Karnaugh maps for F1, F2 and F3. Karnaugh map is an advanced technique which help us to derive boolean expression for any circuit very easily. So from this Karnaugh map I gonna make a boolean expression for F1, F2 and F3. Here you see the boolean expressions of F1, F2 and F3 from Karnaugh map. Now this boolean expressions are simplified and I can make the circuit on Proteus very easily from these boolean expressions. Now I am showing you the circuits that I make on Proteus for 2-bit comparator. This is the circuit of 2-bit comparator using AND gate and XOR gate and OR gate only. Here the LED 1 is for F1 which shows that when N1 is equals to N2 and LED 2 is for F2 which is N1 is less than N2 and LED 3 is for F3 which is N1 greater than N2. Here are the inputs A, B, C and D and now all the inputs are 0. This is the circuit for this is the circuit for F1 which I make from boolean expression of F1 using 2 XOR gates and 1 AND gate. And here you see the boolean circuit of F2 which is N1 is less than N2 and I make this circuit from boolean expression of F2 using 3 AND gates and the output of these 3 AND gates is combining at OR gate, and this is the circuit for F3 using 3 AND gates and OR gates which I derive from boolean expression. Now we can make a 2-bit comparator using NAND gate and NAND gate only, for which we have to convert these AND gates into NAND gates and these OR gates into NAND gate. Now I show you the technique which I use to convert the AND gates into NAND gates and these OR gates into NAND gates. To convert the AND gate into NAND gate we use this technique which shows when we have to convert the AND gate we use 2 NAND gates and we join them in this technique to convert this NAND gates into AND gate, and to convert the OR gate into NAND gate we use NOT gates and NAND gate as shown in this figure. So from this technique I make this 2-bit comparator of AND gate and OR gates into this 2-bit comparator using NAND gates only. Now using this technique, I convert all the AND gates into NAND gates and all OR gates into NAND gates. Here you see these AND gates which are derived from AND gate. I convert all the AND gates into NAND gates. Here you see the AND gates and NOR gates which I derive from OR gate and convert OR gates into NAND gates. Now when I run the circuit, here you see when all the inputs are 0 and 1 is equals to N2 now, so F1 runs, which is N1 is equals to N2. Now when I change the input and I input to I give the high input at B, which means our now F1 now N1 is greater than N2, so our LED 3 glows, which is F3, and N1 is greater than N2. Now when I hide the input A, now all the inputs are 1 and again F1 glows, which is N1 equals to N2. Now when I hide the input A only and lower all the output, so F3 includes, which is N1 is greater than N2, and now it's also N1 is greater than N2, and similarly D is 0 and all the inputs are 1, which means N1 is still greater than N2 and F3 glows. Now you see when I hide the input C and low the output B, LED2 glows, which means that N1 is less than N2, and similarly when I give high input D, also F2 glows, which means that N1 is less than N2. So from this simulation you can see that we can easily make a 2-bit comparator using NAND gates only. And we can convert all the AND gates into NAND gates, and you see that our task is complete. So we conclude that in order to make any circuit, first of all we know the block diagram of our circuit, and from this we can make a truth table, because truth table is very essential for every circuit. From truth table we can see the outputs and input relations. So in order to make a boolean expression, we make Karnaugh maps, because Karnaugh maps is a very essential method for boolean expression. We can easily make a boolean expression for Karnaugh maps. So from this, in this task we can make all these steps, and at the end we can we make a circuit on Proteus and simulate it and see our outputs. Thank you for watching the video.